So on the exams, you can see everything now. So we have the midterm solutions. You should be able to go to Code Assessor, to the CS102 Dev website. You should be able to see your answers at this point. If you can't, let me know, but you should be able to see the code that you entered. In general, you did very well on the coding problems. The median was an 88. That was very good. There's just, on each of them, there were a few smallish things that we need to talk about. Just because we are trying to teach you to be more logical in your thinking, and also we're trying to teach you to really think about efficiency. So with the deleting of the codes, most of you did quite well in this problem. You got the idea that you could make one pass through it. A number of you made multiple passes, so you lost 5 points for making multiple passes. If you have so you were guaranteed that the two lists were in sorted order. So if this was the used codes list and this was the outstanding codes list, then let's say this was like AX, BY, maybe D, N, and maybe on the outstanding codes list we have AB, AX, BY, C, Z, D, N, and EF. So since they are both in sorted order, you can start your two iterators at the first element and then move the iterator for the outstanding codes forward until you find the first code that matches one from the used list, and you delete it. And you use the erase method to advance the iterator to here. And once you've done that erasing, you also advance the used iterator. And again, they match. So you again erase BY. Advance both iterators, and now the outstanding codes iterator is less than the used code, so again you advance it until you match a code, delete it, so on and so forth. So one pass order N. So if you made multiple passes where you reset the iterator for the outstanding list all the way back to the beginning, you got 5 points taken off because that's an order N squared algorithm. You're making N passes through the outstanding codes list rather than just a single pass. Okay, the second issue is that most of you iterate it to the end of the outstanding codes list, but that's inefficient. Okay, you were told that the used codes list was a subset of the outstanding codes list. So you knew for a fact that the outstanding codes list would be exhausted before the outstanding codes list. So the efficient thing to do was to iterate to the end of the used codes list. Okay, so you lost a point for iterating to the end of the outstanding codes list because that's not efficient. Let's say the used codes list is empty or has only one element in it. Then you could very quickly find the code that needs to be deleted in the outstanding codes list, and you could immediately terminate rather than spending a lot more time walking all the way to the outstanding codes list. So this is what I mean by we want you to think logically. We want you to think through the implications of the information we give you. And in this case, when we tell you that the used codes list is a subset of the outstanding codes list, then you know the used codes list will be exhausted first. And some of you were having tests, conditional tests, where you said, well, if I get to the end of the used codes list first, or I get to the end of the outstanding codes list first. And again, you lost a point because it's impossible to get to the end of the outstanding codes list first, effectively. So it's just a useless conditional. So that's the other thing that we just don't want you doing. We don't want you putting tests that have no value in your program. Okay? Conditionals that always evaluate to true, conditionals that always evaluate to false, those are conditionals that just waste the CPU's time and they don't accomplish anything. So we just want to, another example of that, putting in a conditional that couldn't possibly ever succeed was one where if you found that the codes iter was equal to the used code iter, some people had a conditional now that said if used iter is equal to used codes, I think mine is used, yep, used codes dot end, break. Okay, else advance the iter. Okay, what's wrong with this conditional? It can never be true. It is always false. It has absolutely zero hope of being true. Why does it have absolutely zero hope of being true? So the condition in the while loop. While used iter not equal used codes dot end. So you wouldn't even be in this while loop if the used iter was equal to used codes dot end. It's absolutely impossible for you to be in this while loop if used iter is equal to used codes dot end. Okay, so you're just making an absolutely, it's useless. There's no point to this conditional. Okay, so we want to teach you again to think logically. So you're getting small deductions for that because I don't want to take off big points, but I want it to sting. Okay, I do want you to sit up and take notice that you shouldn't be casually putting conditions in your code that can't be possibly true or can't possibly be false. Okay, the other thing, many of you lost a point for not using meaningful variable names. I had to grade 80 of these. Okay, when you use such meaningful names like iter1 and iter2, it's meaningless to me. I'm sitting there thinking, okay, is iter1 the codes or is iter2 the used codes? I don't know. I keep having to look up to the top. Okay, or if you say it and it1. Okay, I'm sorry, but those are meaningless names to me. They don't correspond in any meaningful way to the codes in the used codes list. So this is another thing. You need to have meaningful variable names. Okay, so again, you lost a point if you were not using meaningful variable names. Even just citer and uiter was good enough. Because citer and uiter, I can tell that uiter should be the used codes and citer would be the codes. Unless, and a couple of you did this, you named an iter citer and then you made it equal to the used codes list. And again, you lost a point because that's just not meaningful to me. Okay, so we do care about using meaningful variable names. But in general, y'all did well in this problem. There was just these kind of little stingy deductions because we just want to make you think about efficiency. We want to make you be more logical with thinking, but didn't want to take away big points when you fundamentally had the right answer. So this was quite good. Where more people lost points, not surprisingly, was on the second problem where you were having students join clubs and you were adding students to your clubs. And for the most part, most of you got the hash one, which was good because it was Lab 5. I was essentially just asking you to implement the separate chaining algorithm that you did in Lab 5. So there wasn't really a whole lot of issues with the hash function. There were more issues with the adding. There was just two, again, small but important issues. One was that with the Join Club, I will say I knew this. If you didn't, it's fine. So if you try to access a student and it doesn't exist, you're not supposed to do anything. And the default value that gets returned if you ask for a student is not there is null. And I didn't care whether that student got added to the tree or not. So I was perfectly happy to allow you to ask for the student. This will add a key value pair for the student to the tree. I wasn't concerned about that because there wasn't any reason to print it out. So you'd get back null, and otherwise you'd insert it. Now, some of you did one find to see whether the student was there. So you did one find to see if the student existed. And then you did another find to retrieve the student's record or a pointer, to receive a pointer to the student's record and add it to club. Now there's an issue. These finds aren't free. They cost order login time, i.e. they're an expensive operation. So repeating them is not good. This is where you do want to save the result and then reuse it. So you lost 2 points if you called find twice, because order login operations aren't cheap. Okay, they're not constant time. So I wanted you to save the result from the find and then reuse that result when inserting. Okay, so you need to be careful about that. Calls into maps or calls to functions aren't cheap. They cost you. It's better generally to save any call that you have to make to a function if you plan to reuse it. Even if it's a constant time function, the overhead of saving the registers, creating a new stack frame, popping the stack frame, there's overhead associated with calling a function. So you should save the return value. The other issue, many of you were writing consecutive if statements for add student and join club. You're saying if command equals add student, if command equals join club, and you lost a point. You need to get used to using else for mutually exclusive statements. This is another one of those small things but important about thinking logically. Add student and join club are mutually exclusive, so you should be using else if. Okay? Again, it's inefficient if you found that the command was equal to add student. It can't possibly be also join club. So doing the else, if I don't have the else here, and the command is add student, then this command is guaranteed to be false. This conditional check is guaranteed to be false. There's just no reason to perform that check. Okay, that's why the else is there. Okay, so we want you to use else statements when you have mutually exclusive choices. Okay, the other stuff was very varied, and there wasn't any other, I guess, huge things that I could really point to as problems. So that was, as I say, quite good. I guess one last thing with add codes. Some of you forgot to pass stuff by reference, okay? And some of you passed codes by reference, but you didn't pass use codes by reference. So you lost 3 points for not passing codes by reference, because if you didn't pass codes by reference, the problem didn't work. You had to modify the list, the original list, not a copy. You lost a point for not passing use codes by reference, because making a copy of the entire use codes list is expensive. Remember, we want you passing your objects by reference. And again, I'm kind of agnostic as to whether you pass strings by reference or not. Okay, in general, it's a good policy to pass strings by reference, but you often don't see that in code, and it's not as bad to make a copy of a string. But in general, it's still better to pass all objects, even strings, by reference. Okay? So if you have questions about the coding problem, please see me after class, because unless it was one of these more simple issues, then it was probably a more complicated thing where I have to go over with you in greater detail what went wrong. I did, after the last exam, have one student tell me that they did not understand the comments I made. So please, if you don't understand the comments I made, either send me some email, see me in my office hours, see me after class, because I mean, the comments, I'm trying to help you with things. This one I was trying to not write quite so many comments. I think I had 3,500 lines of comments after the last exam, and that really slowed me down. And I was repeating things a lot. So if you're wondering what some of the things like 2.b.3 means, there is a grading guide, and the grading guide at the bottom has the reasons you lost points. So if you say something like 2.b.3, it means question 2, part B3, you lost 2 points for calling find twice rather than just once. So for this exam, when I found commonly missed problems, I simply put that explanation down and then put a code effectively in your comment so you could find it in the grading guide. Okay, and the grading guide has all the different deductions for everything that happens. So hopefully Lou will have that stuff up very soon, and you'll be able to at least see your paper portion of your grades. Okay. Before I forget, let's see if I can. There is a just brief announcement if I can. Might not be able to. Okay, well, I can't get it up, so this afternoon, now I have nothing. So this afternoon at 4 o'clock, there is a presentation. So today, MinGal 406 at, this is 406, at 4 p.m. There's a presentation by Nadine Laloff, sponsored by Sisters. And she is talking about successful women in tech. She is works for a company called NIT. So encourage you to show up. That's open to everyone. So again, MinGal 4:06 p.m. today, November 13th. Okay, so Sisters periodically puts on presentations like this. I'm not sure if they're serving food at that. Is there anyone from Sisters here that can tell me whether there's food or not? Okay. So won't make any promises as to that. So, okay. So, we spent the last 2 days talking about recursion. And we presented 2 different reasons for using recursion. One was simply breaking problems into smaller subpieces and then recombining the results because it's good for parallelization. On Lab 9, you're doing something where you're enumerating strings of zeros and ones. It's good for breaking that problem into pieces and recombining. We also saw with the recursive Sudoku solver how you could use it for backtracking to solve search problems. Over the course of the next 3 weeks, we're going to see how you can use it to search trees, which are the way that sets and maps are implemented in the STL, and in fact, in general, how they are implemented. So trees themselves are recursive data structures, and you should be somewhat familiar with trees. A couple common example of trees, family trees. So you may have seen, like with royalty, you'll see like William III and Elizabeth II. Well, not Elizabeth II, but maybe Elizabeth IV. And then you see their offspring. Okay, Julia and Anthony and Peter. Okay, and then you may see some other things, again, like Julia married Marcus, and Anthony married, I don't know, Nancy, and Peter never married, and they begat. Okay, and so on and so forth. So you've seen family trees. Okay, so the idea is there's a root. Okay, it's the top of the tree, and the trees are inverted. Rather than growing up from the tree up, they grow from the top down. And they have leaves. So the leaves are the things with no children, the nodes with no children. So they are the current in the family tree. They are the living people right now, and all the ancestors are higher up in the trees. We call all of the non-leaf nodes internal nodes. So internal nodes have children. Leaves do not have children. All nodes have a parent except for the root. The root's the only one without a parent. And all nodes have exactly one parent. They don't have 2, they don't have 0, they have 1. Except for the root. Okay? And then we talk about the depth of the tree. Actually, we talk about the depth of a node. Okay? And that is the number of edges from the node to the root. So for example, if I had down here a child of Julia, might be Smiley, then Smiley's depth is 1, 2. So Smiley's depth would be 2. And we often talk about the height of a tree. So we talk about the depth of a node, but the height of a tree, so the entire tree. Okay? So it is the length of the longest path from the root to a child. Another way of thinking about it, it is the maximum depth the height is equal to the maximum depth of any node in the tree. So another way of thinking of height is it's the maximum depth of any node in the tree. So in this case, Smiley right now is the maximum depth, although really any child here, if I had B, C, D, E, F, then really all of them have depths of 2. So these are the important definitions: depth, height, root, internal nodes, leaves. I don't have leaves right here, so leaf nodes. And then we often talk about parent. That's the parent of some child. We often talk about parent and child. Okay, so family trees, you have probably seen such a thing. If not, perhaps you have seen an organization chart. So we have like the president of the UT system. Then at the different campuses, we have the chancellor. So we have like the chancellor at UT. We have the chancellor at UTC. There's a chancellor at the UT Medical School. Then we have our provost. And we have other sub-people like I believe the athletic director may be under the chancellor. And then under the provost, we have the various deans. So like the engineering dean and the A&S dean, so on. So organization charts are an example of trees generally. Normally you don't have 2 bosses. Normally you only have one boss. That would be your parent. There's the big honcho who's the head of everything. That's the root. Okay. So these are, and trees are recursive structures. So every child is itself a tree. So in a tree, every child is a tree. So every child is itself a tree. So we call it a recursive structure. A tree, hence a tree is a recursive structure. Okay, remember recursion, we separate a task into identical but smaller subtasks. So a tree is children. Each children is a tree, so a smaller tree. And then we combine them all as the children into a bigger tree. And the base cases, there are 2 base cases with a tree. So the base cases are 1, the empty tree, so you're allowed to have an empty tree. And 2, you can have a tree with a single node. In that case, the root is a leaf. So those are the 2 base cases. You have an empty tree and a tree with a single node. Okay. So Dr. Planck's notes has a 3rd example of a tree. This one used to represent expressions. So here we have the expression 5a plus 10b divided by 14 times a to the 4th power minus 28 times b. Again, that can be represented as a tree, the division, and then there's the 2 sub-expressions. So this one here represents 5a plus 10b. This one represents 14a to the 4th minus 28b. And then you can further break it down. So for 5a plus 10b, this is 5 times a. This is 10 times b. And then at the leaves, you have 5 and a, okay, which are the base cases. So it's not so uncommon to represent in a compiler, when you parse an arithmetic expression, the compiler actually tends to represent your arithmetic expressions internally as a tree. And then it generates assembly code from these instructions, because you covered assembly code in 130. You can't write in assembly code this expression. You have to write very simple operations like plus, minus, divide. So representing the expression as a tree, it's then very easy to generate assembly code from this tree. For example, to do 5 times a, you first load into, say, register 1, maybe 5, then you load into register 2, perhaps a, then maybe you multiply, put the result into register 3 of register 1 times register 2. So it makes it very easy with this tree to start generating these short assembly language instructions, because generally assembly language instructions have at most 2 operands. Okay? So that's how compilers, you may wonder how compilers go about generating assembly code. This is one example. They represent arithmetic expressions as so-called expression trees. We call these expression trees. And they generate the code by walking the tree. So now we have to talk about walking the trees, but first, yes. So there's 3 ways that you can walk a tree. Okay, so we talk about walking or traversing a tree. Just like you traverse a list or you traverse a vector, you'd like to be able to traverse the tree. So there's 3 ways to do it. We call it pre-order, post-order, in-order. Okay, so in pre-order, we first, when we visit a node, we perform some action, like say print, and then we recursively visit the children in order. So if we were printing this tree, then if we were doing it in pre-order, we would visit the root and we would print it. So we'd perform the action first. So we would print the divide. Then we always visit the leftmost child first. So we visit plus. And again, the first thing we do is print plus. And then we visit the left child, which is times, and we print times. Then we visit its left child, which is 5, and print 5. Come back up to times. It has not exhausted its child list, so we go down to A, print A. Come back up to plus. It has not yet exhausted its child list, so we come down to the next child, and so on. So in general, the way that we traverse trees is top down from the root, left to right. So we visit the leftmost child first, rightmost child last. So all 3 traversals, whether they're pre-order, in-order, post-order, will all follow this traversal pattern. The only question is, do they perform an action when you visit a node? You can perform action 1 before visiting any children. That's pre-order. Or we can perform the action after visiting all children. That's called post-order. Or in the special case of a binary tree where there's at most 2 children, between visits to the left and right child. So that's special case. It's supposed to be children. The last one is a special case. It applies only to binary trees. Does not apply. So the first two apply to any type of tree. The last one is a binary tree we'll talk about in a moment. It's limited to at most 2 children. So if we do a post-order traversal and we were printing this tree, then we would start by our visit. We'd visit L, but we wouldn't do any action until we had visited plus and minus. So in fact, whatever gets printed out would be printed at the very end. So we'd first visit plus, but before doing any action, we would visit times. But before doing any action, we would visit 5. So the first thing that would get printed in post order is 5. Then what would be the next thing we would print in post order after 5? It would be A, because in post order we visit all the children first, so we would visit A. Once we've visited all of the children for times, now we print times. Okay, now we come back up to plus. If we're in post order mode, we don't yet print plus because we haven't visited all the children. We now come down to its right child. And again, we haven't visited yet all of times's children, so we'd end up printing out 10B before we printed out the times. So that prints this tray. Now when we come back up to plus, we've visited all of its children, so we print plus. So that's post order. Okay, and finally, in order is how we would actually be able to print the expression so it looked like that. Okay, so in order, we would first visit the left tree and print all of the left tree. Then we would print this middle node. Then we would print the right tree. So if we were in order, we would again start by visiting the left tree, and it would visit its left, and it would print 5. But now in order, when we come back, we are going to print the node, because in order between visits to the left and right children, we perform our action. So we would now do our times. Now we would come down to A and print A. So we're done with this tree. We come back up to the plus, and again we're in the middle. So we print the plus, come down to here, and if we're doing it in order, we do the 10 first, then the times, then the B. So you can see we're getting it in the same order that we had it up here. So 3 kinds of traversals are pre-order, post-order, in-order. They all are top down from the root. They all are left to right. So if I wanted to evaluate this expression tree, let's say that I also have values for A like 3 and B has 4. Let's say I wanted to go through this expression tree. I wanted to traverse it and evaluate this expression. So when it's done, I actually want a value. The question is, which of the 3 traversals should I use if I want to produce a value? Okay, so let's have a vote. How many, we'll start from the first one we considered, how many think we need to do a pre-order traversal if we want to evaluate this tree? Uh-oh, hope that's not right. Okay, how many think we need to do a post-order traversal? Come on, be bold. Get them up there. Rachel, get that hand high. Okay, and how many think it's in order? Get them high. Be proud. Okay, so it is post-order. Okay, the reason it's post order is you can't evaluate the division until you know the results of both the plus and the minus. Okay, I'll make it a little simpler. That was kind of a complicated one. So let's just say that I had plus A times 10B. Okay, so if I do pre-order, I can't evaluate the plus at all because I don't know what the value of either the left or the right expression is yet. If I try to do in order, I'll know what the value of the left subtree is. If A is 5, I'll know that the value of the left subtree is 5, but I still won't know the value of the right subtree if I do in order. If I do post order, then I will visit each of the children first, so by the time I come back from the children, I'll know that the left subtree is 5 and the right subtree is 30, and I can do my addition at that point. So that's why I need to use post order to evaluate an expression tree, because I need to visit all of my children first in order to know what their values are before I can apply the operator, the arithmetic operator, to combine the results. Okay? This is also how the compiler would generate assembly code. It would first have to generate all the assembly code to generate the value of the expression on the left. Then it would have to generate all of the assembly code to generate the value of the right expression. And only when it had those two values in registers would it be able to generate the assembly code to combine those two. So in fact, when the compiler generates assembly code for this arithmetic expression, it also uses a post-order traversal of the tree. Okay? Now, here's another example. Let's say we have this tree where we're going to assume everything is in sorted order, which means we're going to assume that in the left subtree, everything is less than 10, and in the right subtree, everything is greater than 10, greater than or equal to 10. And we will also assume that in any subtree, so we'll assume that in any subtree rooted at x, that anything in the left subtree is less than x, and anything in the right subtree is greater than or equal to x. And now I want to print everything out in sorted order. So if I print this tree, I want to print it as 2, 5, 7, 10, 13, 15, 18. And the question is, should I use a pre-order, a in-order, or a post-order traversal to do it? So again, the polls are about to open. How many vote for pre-order? No one. How many vote for post-order? Come on. We can't have absentee ballots, or not absentee, abstentions. This is a republic. We want everyone to vote. Okay, in order. Madeline, get your hand up. All right. In order is the way. So, in this case, we want to print everything less than 10. Then we want to print 10, and then everything greater than 10. So if we're doing it if we want to print that tree in sorted order, we need to use an in-order traversal, because we want everything, we guaranteed that everything less than 10 is in the left subtree. Then we print 10, then we know everything greater than 10 is in the right subtree. So in order is perfect there. Okay? Yes, John?
In the side book, it has less than equal to on the left and has greater than equal.
Yes, but in Dr. Planck's notes, he is using greater than or equal on the right side, and that means that in his labs and all his stuff Cody gives you, he is assuming that all equal values go to the right side. So it's arbitrary. You can put, you need to be consistent. You don't want to put equal values in both the left and the right subtrees. You want to put either all of your equal values on the left side or all of your equal values on the right side, but it's a coin flip. Okay, so the book chose left, Dr. Planck chose right.
The book says it's equal if you go in either one.
Well, the book is
So it's like,
not, this is, okay, the reason why that is dumb, okay, is that if you say that you're looking for something like 10 and you want all values of 10 and you've put 10 in either the left or the right subtree, you have to search both halves of the tree. Whereas if you know that equal values can only go in the left subtree or the right subtree, you only have to search half the tree. Okay? So I don't know why the book said it that way, but I'll repeat, that's dumb.
I just wanted to make sure.
Okay, yes. So you either put, in general, you put all of your equal values in the left or you put all your equal values in the right, but you make that decision and you stick with it. So is that what you were going to say? The book said it could go on either? Okay.
If you're traversing in order and there are an odd number of children, what happens?
Odd number of children. You mean like here I have 1 so that there's 4 children on the left, and or is that not what you mean by odd number of children?
Yeah, I was thinking more like if 5 has 3 children.
It can't here. Okay? So in order applies only to binary trees.
Oh,
It doesn't apply, and so binary trees are special trees. They can have at most 2 children. Okay? Which is why we can get away with saying in order is done between the visit to the left child and the right child. Okay? In order only applies in the special case of a binary tree. So don't worry about 3. And then it is possible in a binary tree to have a, quote, odd number. It means you have either a left child or a right child, but it's well defined. Here, 1 is the left child, so you would visit 1 first, then you would visit 2, and then 2 has no right child. So there's no visit to the right child, okay? So, other questions? Okay, so in fact, that is what we will be concentrating on in this course, are binary trees. And specifically, we will be concentrating on something called binary search trees. And they have exactly the property that I just talked about, which is that in the left subtree, all values, so binary search trees, okay, have the property that, first of all, at most 2 children, so 0, 1, or 2 are all legitimate. 2, all values in the left subtree are less than the root. All values in the right subtree and, okay, all values in the right subtree are greater than equal to the root. And it's arbitrary whether the equal values go in the left side or the right side. Dr. Planck's notes use the right side, so we'll use the right side. So it is easy to locate values in a binary search tree. Okay, so all you have to do in a binary search tree, let's say we're trying to find Luther, is we look at the root node, and if Luther is greater than Binky, which is the case here, where must Luther be? The left subtree or the right subtree? It must be in the right subtree because the only values that are greater than Binky are in the right subtree. There can be no values greater than Binky in the left subtree. So Luther must be in the right subtree. So we go to the right subtree. And we compare Luther with Fred. And Luther is greater than Fred. So where must Luther be? In the left subtree? How about the right subtree? There we go. Because all values that are greater than Fred are in the right subtree. There is not a single value greater than Fred in the left subtree. So if Luther exists in our tree, Luther must be in the right subtree. And there is Luther, right child of Fred. Okay? So it's pretty easy to find nodes in a binary search tree. You start at the root. If it's equal, well, we found it. If it's not equal, we say if it's less than, it must be in the left subtree. If it's greater than or equal to, it must be in the right subtree. Okay? Now, you'll notice some things about binary search trees. These two are different binary search trees but have the same values in them. They're both legitimate. Okay? And they result because we presented things in different order. So in this one, we presented input in the order Fred, say, Luther, Binky. In this one, we presented it in the order Binky, Fred, Luther. Because insert goes like this. We start in an empty tree and we simply add Fred because there's no node yet. So in an empty tree, the first insert becomes the root. But thereafter, we are going to traverse the tree. So we want to add Luther next. Should Luther go to the left of Fred or to the right of Fred? To the right, because Luther is greater than Fred. Luther must go in the right subtree. Fred has no right child, so we add Luther as a right child. Now we try to add Binky. Binky is greater than Fred, less than Fred, equal to Fred, less than Fred. So Binky goes to the left tree, and since there's no further node, that's where Binky goes. Let's try another one. You try this for a moment. Where should Daisy go? Just take a moment. You can even talk about it with a friend. Where do you think Daisy goes? Don't just give everyone a moment to think about this. Where does Daisy go? Someone want to give us the answer? We're all so shy. Right of Binky. Very good. Okay. So, questions about that? Yes, Rachel. Okay, let's move on then. No, I'm kidding. Go right. There are no stupid questions. Go right ahead.
When coding, can we assume that when we use the terms right and left, you're speaking from the programmer's perspective, not the computer's perspective?
Yes, I see what you're saying. You can think that you are from the programmer's perspective is good. It turns out that I see what you're saying because the computer is kind of like that, but the computer kind of sees it as right and left too. So, yes, definitely take the programmer's perspective. That would, okay. So, other questions? Okay. If there are no further questions, you get to do it. So, that's right. So let's do Nancy and Tanya. And I don't know any other skaters from that era. Let's see. Scott Hamilton was a good one. Who else are good skaters? Dorothy Hamill. None of you remember her. I was even young. Dorothy Hamill was 1976, gold medalist. Oh, this is a new tree that you all are going to do. Give me some names of skaters. Good ice skaters. Champion men, women, or... Really? No one? Yes. Pardon? Okay, spell that one for me. Y-U-R... Okay, we'll just say Yuru. Okay, I need one more. Let's see. We'll do Adam. I'm sure Adam was. And finally, we will end with. You want who? Bob? Okay, we'll do Bob. Okay, so they're presented in this order. Yuru is presented after Dorothy. So I want you to. I wish I'd brought scrap of paper. For those of you with scraps of paper, please do it. For those of you who have a computer in front of you, look at a neighbor and work with a neighbor. Okay? If you don't have a neighbor with a piece of paper, see if you can't work it out using ASCII art. So draw the binary search tree that results. Yes. If I wasn't clear, you're starting from an empty tree. Okay, so here we go. So Nancy is our root. Tanya is greater than Nancy. Okay, Scott is greater than Nancy, but less than Tanya. So it becomes a left child. Dorothy is less than Nancy. Yuru is greater than Nancy, greater than Tanya. So goes here. Adam is less than Nancy and less than Dorothy. And finally, Bob is less than Nancy, less than Dorothy, greater than Adam, and goes there. So that is our binary search tree that results. Are there questions about this? Yes.
So if the first one you insert is the root,
Yes, so let's say that instead I gave you Adam, Bob, Dorothy. What was, let's next in alphabetical order, Nancy, Scott, Tanya, and Yuru. Okay, this would be bad. It would be very skewed. So it would be Adam, Bob, Dorothy, Nancy, Scott. In other words, it would essentially be a linked list. Okay? So insertion order in binary search trees is very important. It's really important generally that the first item you insert be roughly in the middle. And if it's not, it's bad. So we will get, this week is unbalanced binary search trees. Next week we get into balanced binary search trees where we talk about how we solve this problem. So with balanced binary search trees, we'll do something called a rotation to try to keep rebalancing things so that we keep it roughly balanced. So you are absolutely right. If the weakness of the weakness of unbalanced binary search trees is they're at the mercy of the order that we give the data. We're hoping it's in random order and that the first items coming in are near the middle. But if they're not, we could get something skewed like this. So in the best case, so one thing we do know about searching is we only do one search at each level. Okay, we look at the root and regardless of what happens, we move to level 2. So we do one search at level 1, one search at level 2, one search at level 3. We never do more than one search at each level in a binary search tree. Okay? So, remember we talked about the height of a tree. Does anyone remember what the height is? Can we think back about 30 to 40 minutes? It's the length of the longest path from the root to a node. So in this case, it's clearly pretty bad. The height of this tree right here is actually order n because there's n items in the tree and the height of that tree is basically n. But if we are much luckier and the tree is very balanced, okay, in fact, in the parlance of the book, we get a so-called perfect tree where the n nodes are inserted into a tree and it's perfectly balanced. The height of the tree will be order log n in a perfectly balanced tree, which means that there will be no more than log n levels. So if the tree is very well balanced, then its height is log n. Okay, you get one node at the root, 2 nodes at the second level, 4 nodes at the next level, 8 nodes at the next level. So that's whenever you're able to effectively have something, you get log n. So for example, if there was 16, so 8 went into the bottom, so there was 8 left. Of those 8, 4 went into the next level, so on and so forth. We're having it, so we get log n. So that's the nice thing about trees. When we're saying that maps and sets have order log n find and insert, we were assuming that they were balanced trees, and because they were balanced, they had no more than log n levels, and since you have at most one search at each level, that leads to a log n search time or a log n insert time. Okay? So we good with that? Okay. I am quickly going to go through delete, but we will then do it again. on Thursday. So let's say that I want to delete Callista. Pretty easy, right? We just delete the node, it looks like. We delete Callista. So if we delete Callista, we simply have, we delete the leaf node. That's the easy case. The next case, so we have three cases, one where it's a leaf. The second case, let's say we delete Daisy. We have one child. If we delete Daisy, what do you think we should do? Promote Callista. Okay, so we simply replace Daisy with Callista. What if we delete Binky? It's got one child. What do we do? If it's one child, we simply replace the root or the parent with the child. So if we delete Binky, we simply get the tree headed at Fred, which is what we see down here in the notes. If we delete Binky, we get this tree right here. So if we delete a node that has one child, we simply replace the node with that child. Okay, the difficult case is when we have two children. Let's say we delete Fred. Fred has two children. What we do in that case, so with two children, find the largest key in the left subtree. Okay? Delete this key, and 3, replace the deleted key with this largest, I'll say largest key. So for example, the largest key in Fred's left subtree is Callista, so we will replace Fred with Callista. And the reason this works is that if we replace the key with the largest key in the left subtree, so this should have said left subtree, then we know that all values in the left subtree are still less than this largest key, and all keys in the right subtree are greater than this largest key in the left subtree. Okay, and we also know that if we delete the largest key in the left subtree, what is the maximum number of children that that key can have? If it is the largest key, it can have at most 1. We're guaranteed that it can have at most 1 key. What would happen if it had a second key? What? I heard it. If it had a second key, this is the largest, and it has a right child. It's not the largest, right? That's logically impossible. So if it's the largest key in the left subtree, it cannot have a right child. Therefore, we know at most it has 1 child, and we know how to delete it. So that's what we do if we have 2 children. I'll repeat this at the beginning of class on Thursday because I know this was a bit rushed. And then on Thursday, we're going to go through a bunch of code. So you're going to see how the code actually implements the 3 operations we have talked about.